Okay, good morning, everybody. There appears to be something wrong with my camera again, and I'm not sure why, but I don't think we need it today, so I think we'll be okay, hopefully. So hopefully everybody can hear me, and let me know if you can't hear me or you can hear me, one way or the other. Before we get started talking about physics, good, you can hear me. Thank you. I wanted to mention that the math department is running what they call their math success session. Oh, someone would like me to put the link in the chat. I will try. Okay, but so they're running this math success session. And so if you would like to get some help with figuring out effective strategies for preparing for math exams, this stuff's usually helpful for physics exams, any kind of quantitative exams. I'm not sure if I can put this link in the chat easily or not. Let me see. Thank you, Ryan. Thank you. So I just wanted to let you guys know about that. And if you have questions, you should talk to the math department because they're the ones that are putting this on. It looks like it's right around the time of our office hours on Wednesday this week. That's one thing I wanted to mention is I'm probably gonna run 2 hours of office hours on Wednesday because we have a test coming up, as you know, on Friday. So I'm going to run office hours on Wednesday from 1:30 to 3:30. So it does overlap this, but you could come to the first hour of office hour, and then you could go to this. So you could do both. It's not a complete overlap there. So the other thing I wanted to share with you was something else about the test coming up. So we all know we have our second test on Friday, and so I updated this page here under tests that talks about logistical information. I changed it to test 2 here. So our test is this Friday at 9:30. And the main thing I changed is so don't worry about, you don't have to re-upload your picture. I have all of your pictures now, so you don't need to do that again. We'll just use those again. We are going to do the Zoom invigilation, just like we did, and that seemed to work out okay last time for most people. The main thing I wanted to do is show you is that I added an extra part here about if you have internet connectivity issues during the test. I know that some people had some issues last time, either with the Zoom session or with Canvas or with both. And so things to do, please, if you are having issues, is to take a screenshot showing your disconnection notice or your slow connection. Canvas will tell you if you're having a slow connection. Try to reconnect as quickly as possible. Make sure to let the person who's invigilating your test in Zoom know that you got disconnected, because while the test is running, I can give you more time in the Canvas quiz if I know during the test that that's happening. If you completely lose connection and you cannot reconnect, then I would like you to start trying to take a video of yourself with your cell phone and just continuously video yourself taking the test. Okay, this would probably work if you're doing the written work at the end, and then show your written work to the camera, and then before you submit it to CrowdMark, once you're reconnected, and we'll figure out a way for you to send that video to me. And if you have problems with your CrowdMark, some people got worried when the deadline passed and they didn't submit. You should just go ahead and submit even if the deadline is passed. It should still let you submit. Okay, and we can work on the deductions later if there was a good reason why you were late submitting. Okay, so what do you want to, for the Zoom links, would you be able to display the meeting room ID and the password? I'll see if I can get the TAs to do that, okay? The TAs are all going to be invigilating the same time, okay? And yes, your camera needs to be open so we can see your face. A couple people, it was kind of dark and we couldn't see their face. We want to make sure we can see your face well. Okay, And if you have any other questions about that kind of question, logistical questions, please put them in Piazza, and I will try to answer them there. Okay. So let's see. Now we're going to get started on some physics. And as you know, we're in the middle of talking about momentum. So we're going to stop sharing this. And we're going to get to our slides. Okay, and that's actually the end. We're going to play from the start. There we go. Okay, so here we go. So we are, so this is a kind of a cute comic where Calvin of Calvin and Hobbes is demonstrating how you can change momentum with a force. Okay, so, and luckily he was able to change his momentum twice and get back to where he started. Okay, so the next topic to look at with momentum is collisions. And as you saw in the pre-lecture videos, there are two main types of collisions. We divide things up into two types. The first type are what we call elastic collisions, and the main defining feature of an elastic collision is that the total mechanical energy, which remember is the sum of the kinetic and all of the potential energies, is conserved. So that means that the total mechanical energy during the collision doesn't change. The change is equal to 0. And this is usually characterized by objects bouncing off each other. So they come in with some kinetic energy, they bounce off, and they go out with kinetic energy. And you look at the before and after kinetic energy, because it's usually kinetic energy that is the quantity that you'll be measuring. You'll see that they have the same amount of kinetic energy before and after the collision. So a nice example of this is billiard balls. Usually billiard balls exhibit elastic collisions where they've got some incoming energy and just as much outgoing energy. And so again, also with these collisions, your total momentum is also conserved. And that's always conserved no matter which type of collision you're looking at. So inelastic collisions. So inelastic collisions are essentially, in a way, the opposite of elastic collisions, as the name kind of implies. So these are collisions where the mechanical energy is not conserved. So the change in mechanical energy is not equal to 0. It changes depending on the type of collision. So almost all collisions fall into inelastic. Elastic is like a special type. In most collisions, you're going to lose some energy, either because objects stick to each other, or they deform, or they otherwise absorb energy. They make sound, which is a form of energy. There's various ways that you can have energy convert. And then the other example of an inelastic collision, quote unquote, would be explosion, where there's energy being drawn from a source, like a chemical source. Okay, so that's another example of a process that would be considered inelastic. So here's an example of an inelastic collision with two cars, and you can see all the deformation that went in, basically caused, you know, the crumpling of the bumpers and the metal. So it requires energy, right? There's work being done there and all of that compression and deformation. We'll talk about deformation and stress and strain later on. And then, of course, explosions. So here's a typical explosion. So I thought we would try some poll questions. So this is our first poll question on different kinds of collisions. And this one has 5 choices. Let's get this going. So go ahead and start reading this one. Okay, so Your roommate didn't know that he was supposed to poke holes in a potato, so this is like a baked potato, before trying to cook it in the microwave. So he has there's a 150-gram potato initially at rest. It explodes into 2 pieces. So here's an explosion. The 50-gram piece travels to the left at 6 meters per second. What happens to the other piece? So we have an explosion here, right? Which means it's inelastic. So energy, mechanical energy, is not conserved, but momentum would be conserved. Yeah, I agree. Potatoes come out better if you bake them in the oven. I like both mashed and baked. Nadia, yeah, 2 devices is fine. I like sour cream on my mashed potatoes. Okay, I think we're gonna maybe do like 10 more seconds here. So 5, 4, 3, 2, 1. Lots of answers coming in here at the last minute. Okay, let's see what everybody thought. So what do we got? We got the majority, the large majority is going for E, that the other piece is going to move to the right at 3 meters per second. And then the next biggest group says it's going to move to the right at 6 meters per second. So we've got moving to the right, which is good. Okay, because that's definitely correct. How do we know that the second piece is going to move to the right? Well, because the first piece is traveling to the left. And if there's only 2 pieces, right, and you want to conserve momentum, and our potato started, right, with 0 momentum because it was at rest. There are no external forces here. It's just internal forces of the steam, right, causing the explosion. So the total momentum after should also be 0. And we know the second piece must move to the right, so that our momentum vectors add up to 0. And we also know that the magnitude of the momentum of the 100-gram piece must be the same as that of the 50-gram piece, right? And that means the 100-gram piece, it's more massive, twice as massive, so it has to be moving 1/2 as fast. And so the answer was E. Well done. So that's how, that's sort of a typical simple explosion problem and how you would solve it. So well done. Okay, so now we have one that's slightly more complicated. So let's try this one, and I will do another poll. This poll only has 3 choices, so that makes things a little bit easier. Okay, so let's look at what's going on here. So we have a block that has mass little m, and it slides on a frictionless surface and runs into a block of mass big M, which is initially at rest. The blocks stick together, and their speed after the collision is half the speed the moving block had before the collision. How do the masses of the blocks compare? So just because they drew one bigger does not mean it has more mass. Okay, it could be less dense, right? Could be made of styrofoam and the other one is made of wood or something, okay? So don't base your answer on the sizes of the blocks. So this is, again, would be inelastic, right? Because the blocks are sticking together. Anytime things stick together like that, then things are inelastic. And again, remember, since it's inelastic, the only thing that's going to be conserved here is the total momentum. So you may need to do a real quick momentum calculation to figure this one out. All right, I think we'll do 10 more seconds on this one. So if you're not sure, go ahead and guess. So 5, 4, 3, 2, 1. Okay, so what do we get? So it looks like, again, we have quite a lot of consensus. So the largest group is going for B, that the two masses are equal. Okay, but we do have a reasonable number for no, big M is less than little m, and we have some big M is greater than little m. So let's have a look at how you would figure this one out. So like I said, you want to do conservation of momentum. So here is our general two-object conservation of momentum expression, where we have the total final momentum equals the total initial. And remember, all those v's are vectors. So in one dimension, they would be either positive or negative numbers. Okay, so now we're going to go plug in. So what do we know? We know the two final velocities are the same. So I wrote that as vfx. Okay, we're doing this all in the x direction. We know that the little m is moving with some initial velocity in the x direction, and big M, its initial velocity was 0. So I plug that in. Then I plug in what the actual value is given. So I know that the final velocity of both objects is v over 2. I know the initial velocity of little m was v. So I set those two equal to each other like that. And then I play around with the math and I solve for basically the masses, and basically what you get is that big M v over 2 is equal to little m v over 2. So that means that the two masses must be equal to each other. Okay, so for you to have half as much velocity afterwards, then those two values have. Some of you probably could have reasoned that conceptually as well, but I wanted to show you how it worked with the math, because this is how you typically will do all of these collision problems, okay, with two objects, is to start with that sum of the two momenta before and after, set them equal, put in all your values. Okay, now there are special cases, and the one special case that they talk about in the pre-lecture is if you have elastic collisions, okay, in one dimension where the second object, they call object B, is initially at rest. Okay, because the tricky thing with elastic collisions is you have to conserve both momentum and mechanical energy, which in this case is the kinetic energy before and after the collision. And the math can get kind of hairy. So as you can see, because you've got all those V's and V squareds, okay? So for this special case of one-dimensional motion with object B initially at rest for an elastic collision, you can solve for these two expressions where if you know the initial velocity, VAI, in the x direction, the initial velocity of object A, you can solve for the final velocity of object A and the final velocity of object B, okay? So basically, you always use the momentum formula. Okay, momentum is always conserved, okay? But with elastic collisions, you also have to use the energy formula. So you have to use both, okay? Now, if needed, sometimes there will be elastic collisions where they give you enough information that you don't need the energy formula. You can solve the whole thing with just momentum. So I would say start with the momentum formula, and often that's enough. And then if it's not enough, if you have too many unknowns, that's when you have to start using the energy formula. And with an elastic, you only use the momentum formula. Sorry, you only use conservation of momentum. So I thought we would try our collision carts simulation again. So I set this one up. Let's see if I can find it here. So this was the one we were playing around with before break, and it looks like this. Hopefully you can see that okay. So what we have here is sorry, just sorting myself out. So what do we have? We have a cart with an initial velocity of 4 meters per second. And we have a second cart that's initially at rest. So this is like our scenario that we were talking about, the special case where the second object is at rest. And in this case, the first object has a mass of 1 kilogram, and the second object has a mass of 3 kilograms, and there is no friction here. These are our special ideal carts. So when we start this going, we see that after the collision, the smaller cart goes backwards and has a speed of 2 meters per second, so in the backwards direction, so minus 2 meters per second. Okay, and the heavier cart moves forward with a speed of 2 meters per second. So what I wanted to do was show you how to use those formulas to make this work. So let's see if I can get this to work. So I have a new toy. Let's see if I can get this to work for you guys, which is I got myself a document camera. So hopefully you can see this. It's a little fuzzy there, isn't it? Let's see if I can get my focus to work. Let's see if this will focus itself. It doesn't want to focus, does it? Try again. All right, that's better. Okay, so what I'm going to do is actually do the math for that one, okay, to show you that we actually get those answers. Okay, so what did we know? So we know for this one that VAIX was plus 4 meters per second. So that was the initial velocity of cart A. And we know that the mass of cart A was 1 kilogram. And we know that the mass of cart B, in our case, was 3 kilograms. Okay? So Now we're going to figure out what were the final velocities. So VA final x is equal to VA initial x MA minus MB over MA plus MB. So it looks like that. Okay. So now we're going to plug in our numbers. So the initial velocity here, this is our +4 meters per second. And then MA was 1 kilogram and MB was 3 kilograms. So we have 1 minus 3 over the sum of the two, which is 4 kilograms. So it looks something like that. And what do we get? 1 minus 3 is minus 2 divided by 4. The 4's cancel. We get minus 2 meters per second, which is exactly what we saw. That cart A, the smaller cart, right, turned around and went back to where it came. So this is the formula that was in the pre-lecture that I just showed you on the slide. And I'll show it to you again in a minute. And this is the one that only works when we're in one dimension and the first object is moving and the second object is at rest. So what do we get here? This one says it's 2MA over MA plus MB. And I will put these written notes in Canvas. You can see them later. So again, this one is +4 meters per second. Okay, and then we have 2 times MA, so 2 times 1 kilogram. And again, the sum is 4 kilograms. And so now we have 2 over 4, or 1/2, and we get our +2 meters per second. Okay, so that's the math. That would be the velocity. It doesn't matter which side you put for initial and which side you put for final. Okay, so if we go back now and look at our collision, we can see that's in fact what we got. We got that the red cart went backwards with a speed of 2 meters per second, so its velocity is minus 2 meters per second, and the blue cart went forward with 2 meters per second. Okay, so that, and yeah, it doesn't matter. These formulas though, when you're writing P initial equals P final, it doesn't matter which one you put on which side, but these particular formulas I'm just showing you are based on a specific definition of initial and final. Okay, so these are the formulas, they're from your pre-lecture. Okay, so these are good ones to write down. Okay, so, and these, yes, this is assuming positive direction is to the right. Actually, it doesn't assume though that the first object's necessarily moving in the positive direction. You have to put in the signs for the V's. Okay, and yes, you would get the same answer using general conservation of momentum. Okay, you would get the same answer. But I'm not sure you would have enough information to solve it. Because it's an elastic collision, there would be too many unknowns. Okay, so yeah, you have to pick a positive direction and go with it, and then stay with that direction. That's generally the case for these. Okay, so what else were we going to look at? Okay, so the next thing we covered in the pre-lecture, which I wanted to talk about, is the impulse momentum theorem. And so now this is looking at particularly what happens during a collision and how the average collision force multiplied, so the sum of the collision forces multiplied by the time acting on one of the two objects that's colliding is going to equal the change in momentum of that object, because during that collision those objects both undergo a change in momentum. So we call this quantity impulse. So when you're looking at a force applied over a time, that we sometimes call that the impulse. And the impulse momentum theory says that the impulse acting on an object equals its change in momentum. Okay, so a force acting over some time will cause a change in momentum. It's kind of like a force acting over a distance, which is work, will cause a change in energy. So there's a similarity between this and the work kinetic energy theorem. So important to remember that both of these are vector quantities. Change in momentum is a vector because individual momenta are vectors, and impulse, right, which is force, a vector times time, is also a vector quantity. The other thing to notice is that typically during a collision, you don't have a constant force. Usually you have something, a force that starts at some time, goes up to some maximum value, and then drops back down, okay? So, it can be quite complicated. If you do more advanced physics, you actually define this instead of as a sum, but as an integral, and you have to integrate over the force versus time. We're not going to do that. We're just going to recognize that, in fact, the impulse is the area under the force versus time curve. And so you can replace that sort of calculation of the area by saying, I'm going to define an average force so that this blue rectangle has the same area as the area under the curve. Okay, and so I'm going to replace the force that's changing with time and say that on average, how big is the force acting during the collision, and say that average force acts for the whole time. Okay, that's not really what happens, but it's a reasonable approximation to what's happening, and as long as the area is the same, you'll get the right answer. Okay, so a nice example of why it's useful sometimes to think about impulse in collisions is this example here. So this is looking at what happens when you drop an egg. And so say you drop a raw egg, okay, and it hits the floor, you know what's going to happen. If you drop an egg and it hits the floor, it's going to break, right? Why? Well, because that collision is very fast. And because that collision is fast, it's very low time involved, okay? But you still have a change in momentum, but you have a low time, so you need a large force to have a given change in momentum. But if you drop the egg instead onto a pillow and it comes to rest, now it's going to have the same change in momentum, but now that's a soft collision. It takes a longer time. And because it takes a longer time, the average force will be lower. It kind of looks something like this. Okay, this is not as extreme as probably what would happen with these two collisions, but the idea is in the first case, you have a skinnier, taller peak. So the highest force, the maximum force acting is larger, but in the second case, because things are spread out, it happens for a longer time, the peak force is lower. And so this is the whole idea behind cushioning, bubble wrap, airbags in cars. Anytime you have some kind of cushioning, something like that, the whole idea is to increase the collision time because that increases the maximum force for the same momentum change. So I thought we'd try a poll question on impulse. So what do we got? So we got 4 choices here. Okay, so we have 2 carts with different masses, and they collide head-on and rebound back the way they came. Could be elastic or inelastic, we don't know. The magnitude, and so the question is, what can you say about the impulses exerted on each of the 2 carts during the collision? Is the magnitude of the impulse on the heavier cart larger? The magnitude of the impulse on the smaller cart is larger? Both impulses have the same magnitude and direction, or the 2 impulses have the same magnitudes but opposite directions. So which of those is true here? So 2 carts, different masses, colliding head-on and rebounding back the way they came. So this is one of our one-dimensional collisions like we were looking at with our simulation. But now we're looking at the impulses that the 2 carts feel during the collision. So that force acting over time. So impulse is the average force acting times the time it acts. And remember, just like with change in momentum, that impulse is a vector quantity. I mean, the speed of the carts would have an influence on how big the changes in momenta are, right? But in this case, we're comparing the two impulses. So in this case, the speed shouldn't influence this answer. Okay, I think we're going to do 10 more seconds here. So if you're not sure, go ahead and guess. Okay, 5, 4, 3, 2, 1. All right, let's see what everybody thought. So we still have, not quite, but almost the majority are going for D, that the two impulses have the same magnitudes but opposite directions, but we have a reasonable size group going for the magnitude of impulse on the smaller cart is larger. Okay, and then also some votes for the other two options. So let's think about this. So basically, the main thing to remember, okay, is to go back to Newton's third law and remember that if these two carts are interacting like this, that they must exert equal but opposite forces on each other, right? Newton's third law says if A exerts a force on B, that B exerts an equal and opposite force on A, and the times would be the same. In fact, if you looked at the little curves, force versus time for each of these, the shape of the curve would be the same for both carts. Okay, so the impulses would be equal in size, but opposite in direction. Okay, because we know those forces are opposite in direction, so that makes the impulses opposite in direction. Okay, so that's how this would work. Okay, well, if one force gets bigger, the other force also gets bigger. The two forces are always equal and opposite. It doesn't matter how fast the two carts are moving. It doesn't matter how hard the collision is. It doesn't matter what the two masses are. This is also true for inelastic collisions where things stick together. Okay, it's always true that the forces will be equal and opposite, so the impulses will be equal and opposite. Other questions on that? you're going to get a chance to play around with this one a little bit this week in tutorial too. So the last thing I wanted to do today was to do an example problem. And one of the reasons I wanted to do this example problem is because this is a problem that combines two different things. It combines conservation of momentum and conservation of energy. Okay, and we'll see this time and again with physics problems once we learn more and more different conservation laws that oftentimes you have to call on more than one of them to figure out what's going on in a problem. So let's have a look at this one. So we have a bullet, a 15-gram bullet with a speed of v, and it's fired into a 400-gram block of wood that's initially at rest on a surface. You can see the little block of wood with mass m. The coefficient of kinetic friction between the block and the surface is 0.25. The block of wood is attached to a horizontal massless spring, one of these special massless springs that has a spring constant of 320 newtons per meter that's initially uncompressed. Okay, so there's no potential energy in the spring right now, right? Because it's not compressed or stretched. The other end of the spring is attached to the wall as shown in the figure. The bullet becomes embedded in the block of wood, which then compresses the spring a distance of 17 centimeters before momentarily coming to a stop. Assume the block does not move during the collision. Determine the speed v of the bullet. So we're going to try and do this problem here, and I'm going to do it on paper and show you how I would solve this problem. So first of all, I want to ask you, so let's just isolate the bullet colliding with the mass. Okay, what kind of collision is that, do you think? Yes, so that's an inelastic collision. Okay, they're sticking together. You're going to lose energy in the process of that bullet pushing its way through the wood, okay, and getting embedded in it. Okay, so it's definitely inelastic. So that means that momentum is conserved, but energy is not conserved. Okay, so we're going to have momentum for that part of the process. But once the bullet is in the mass and the mass starts sliding, then we can start looking at energy considerations. But now, of course, we've got friction, so it's not going to be conservation of energy because we're going to have to include the work done by the non-conservative force, which is friction. So let's switch over to our camera again. So hopefully everybody's seen that problem. All right, so now I'm going to switch over to my document camera again. Okay. So what have we got? We have, just to write down all of our values again, our bullet has a mass of 0.015 kilograms, 15 grams, right? Okay, that one's a little bit fuzzy again. Let's see if I can get this to focus again. It seems to lose focus. There it goes. Okay. So I'm going to use big M for the block. And that's 0.4. I should have labeled it big M. I'll try and fix that in the picture. I should have labeled it big M in the picture. Okay. So, and we know that our coefficient of friction, kinetic friction, is 0.25. Okay. And we know that our spring constant, so I'm writing down everything I know, 320 newtons per meter. And I know that eventually my spring is going to get compressed by an amount equal to 0.170 meters. Right? That's our 17 centimeters. Okay? All right. So yeah, I used to always do working through problems this way, but I didn't have a document camera until now. So I will switch to this. Okay, because I much prefer this too. Okay, I just did not have the equipment to do it this way before. So anyway, so we're going to start with the collision. So we're going to start with the big block M and the bullet. We're trying to find this speed, right? Okay. And remember that this guy is hooked up to a spring. So what we're going to do is start by writing down, so M is the big block, that's 400 grams. So we're going to start by writing down what happens during the collision, which is where we know that momentum is conserved, right? So that means that the starting momentum, which is m times v, and notice how since things are moving to the left, I'm going to make that my positive direction. Okay, so I'm gonna, you can do this if you want. I'm gonna make that my positive direction. Okay, since things are drawn moving to the left. Okay, so I've got m times v, and then afterwards, the two are stuck together, so I have m plus m, and I'm gonna call this v. Okay, because it's probably reasonable to think that after the bullet, so say afterwards, here's the bullet, this is right before it starts compressing, that it's moving with a velocity v. Okay, technically these are vectors, okay, but because it's one-dimensional and they're in the positive direction, they're just going to be positive numbers. Okay, so we know that that's true, right? And so we have, let's see, what do we have? We have this mass, this mass, this mass, okay? We don't have either of those velocities. So we can't solve for anything yet. So that tells me I need to keep going and figure out what else I know is true, which is I can start looking at the energy considerations. So let's look now at the compression of the spring. And I know that I can now consider the energy situation here. And I know that the initial energy of the bullet block system, so remember this is m plus m now here, okay, plus the work done by the non-conservative forces, which in this case would be the friction, it would be equal to the final total mechanical energy of the system. Okay, and so what does this look like? So the initial energy here is the kinetic energy of the bullet in the block, which looks like that, 1/2 the sum of the two masses times v squared. And now I want the work done by friction. So we've done this a bunch of times, so I'm just going to say I know what that looks like. I know friction does negative work, right? Because the friction is acting, the kinetic friction is acting in this direction, opposite the velocity, okay? And it's just equal to mu k times the normal force, so it looks like this. It's minus mu k, m plus mg is the normal force, because the weight equals the normal force when you're on a horizontal surface, times x, where x is how far my block is going to slide. Okay, because eventually the final scenario is going to look something like this, where the spring is compressed, the bullet and the mass is like that, and the whole thing has slid, right, from where the original collision was, say we call that x equals 0, okay, to some final x, right? So it's compressed by this amount here. Okay, so that's my x there. Okay, and that's got to be equal to, now the spring is compressed, it's momentarily at rest, it's not moving, no kinetic energy. The only energy we have is the spring potential, and so that's equal to 1/2 kx squared. Okay, so that's my statement of energy considerations, okay, of what happens to the total energy when we've got our non-conservative force acting. So now I just have to play around with the math, okay? And so I can, for example, play around with this equation here. So now I'm going to switch to another page because I don't have a lot of space here. So I'm going to switch. Yeah, I will post these on Canvas. So what do we got? So we have now our kinetic energy, which is 1/2 m plus m v squared is equal to, therefore, 1/2 kx squared plus mu k m plus m gx. Right? I just moved that to the other side of the expression, and then I can solve for an expression for v squared. And so what do I get? I get v squared equals 2 1/2 kx squared plus mu k m plus m gx, all divided by the sum of the two masses. Okay, and so now I actually have all of these values. I have k, I have x, I have both of the masses, I have mu k, I know j. So I can actually solve for this. Okay, so we've run out of time, so what I'm going to do is I'm going to plug in all the numbers and show you how to solve for this, and I will put it all into Canvas so you can see. But once you've got all these numbers and you solve for big V, then you just go back to this expression, and once you know big V, you can get little v. Okay, so I'm going to stop there because we have run out of time, and I'm going to stop our recording here. So let's stop the recording.